I just want to confirm the date for the exam. It's Tuesday, correct?
I believe that's what it says on Blackboard. So
I just want to confirm because last time when I looked at exam 2, which I think was Thursday, it didn't say anything on the page. It said like no content or something. Let me check one more time.
wow, my audio just ended. Can you hear me?
Yes, sir.
Okay.
We can hear you, yes.
All right. So I think I'm sharing my screen. Nothing's working, right? So that must mean I'm sharing my screen. And here
Yes, your
is
screen is shared, sir.
here's the syllabus, and the exam is, I think that date is wrong. No, that's right. It's Tuesday. I thought today was the 29th. I'm off by a day. So on the 30th of March, exam number 2. And as everybody's checking in, let me get back to my practice for today. And let's see. Oh, it looks like it's almost the usual, I'm gonna say, gang of crazy people. Now, where is my Zoom info? There it is. How come it's not showing me what I want to see? Chat box is open. And everyone's bling-blonging in. Participants list is shown. I guess I can close that. And we'll go as long. We have an hour scheduled. I'm not sure how long my Zoom connection will hold up. I've had Zoom Pro for several years, and all of a sudden they're refusing to take my money. So I tried a couple times, and to hell with Zoom if they don't take it. We'll be switching to Microsoft Teams next week if we have to. Okay, so there's 11 people here. It's 5:04. There's 12 people here. It's 5:04, and time for wonderful Wino Radio, big sound in the big town. Now, before we start any form of review, are there any specific questions that anybody attending this afternoon has to ask? Because if you have them, someone else has them. I will save you the trouble of what's on the exam. It's what's stated. And what do the problems look like? We will address that today. But any other questions? I guess everybody's microphone is broken, huh? Your videos too. Well, okay, I created a practice workbook for exam 2, and by way of training, when you the in-class portion is much the same structure as the first one. So it'll be a sequence of multiple guess questions. You do better if you guess correctly. There's sufficient time to probably do the multiple guess entirely 2 times, depending on how fast you can read and think. So there's no point in reviewing for that. The topics that we've had since the last test are largely data modeling and hypothesis testing, and that's pretty much it. Okay, what is Weibull? Is that how we check for normality? So Weibull is a formula that allows us to associate estimated probabilities with the rank of a sample. So the rank of an entry of an example. We don't use Weibull to check for normality per se, because the Weibull plotting position formula literally doesn't care what the underlying distribution is. Although it tends to work better if the underlying distribution is log normally distributed, but it doesn't care. Weibull is one of an infinite number of plotting position formulas. So Weibull, we use, checking for normality is a specific hypothesis test. So let's go back to our lessons and figure out which one that is. So we introduced hypothesis testing in lesson 14, 15, 16, and 17. So I'm going to guess our first introduction to hypothesis testing is either lesson 13 or 14. Let's look at lesson 13 and see what there is to see. Oh, that's right, lesson 14. That's the whole counting thing. Oops, wrong one. I want the HTML. Actually, this is good we went here because we'll need this in a second. So when we looked at determining whether a distribution was normal, we did normality test, I believe, in the lab associated with this, because I don't think I talked about normality test specifically. So it must be in the lab that's associated with it. And I don't have the lab conveniently in a notebook, but 14. Yeah, this will have normality tests in it. So in our lab 14, remember Will Smith was hitting you with the flashy thing to make you forget? And one of the tests we have for normality is named after, who can read their own screen?
Shapiro-Wilk.
Excellent. So the Shapiro-Wilk test is a way to test a list for whether its underlying distribution is normal, is likely to be normal or not. So that's how we test for normality. Next question is, what is a CDF? A CDF is a cumulative density function, and I just had that up on the big show. So let's go back here. So it should be lesson 14. And in this picture, we have the red markers, upside down triangles in this case, are a normal distribution data model. So these red markers, when they look like the red markers, and the giveaway is usually the vertical axis doesn't completely go to 1, that is a density function. So as we start from negative infinity and move to points that are larger than negative infinity, for example, if we integrate from negative infinity to -5, this red curve, what's the area under that red curve?
It should be 1.
From negative infinity to -5, what's the area under the red curve in the picture?
0.4?
I would say it's pretty darn close to 0. You're not thinking my question out carefully. If we integrate from negative infinity to 0 on this red curve, what is the area under the red curve from negative infinity to 0?
Negative like 0.45 or something like that.
It's a half, you're correct. If we go from negative infinity to, say, 1.25, about where my cursor is, the area under the red curve?
About 0.25-ish.
No, you go up here, it's about 0.8.
Oh, okay.
So the
Okay,
blue
so we're-
curve, which represents the integral of the red density function as we're moving from negative infinity towards the right, is the cumulative distribution function. The probability density function is the red curve. They are related to each other by an integral differential relationship. The integral of the red curve as you move from left to any arbitrary point on the right, indicated by the value of the random variable axis, is the blue curve. The first derivative, see if that's right, that's integral. So the derivative of the blue curve, I'm not really sure how you do that from minus infinity to some arbitrary point, is the red curve. So one is the integral of the other. So the blue curve is the cumulative density function in the case of a normal distribution. We don't necessarily have to have a distribution model. We can approximate cumulative density functions from sample data, and that's what our friend Weibel does. So the plotting position gives us a way to represent graphically the value of the random variable versus the accumulated estimated probability from the sample. So if we have the entire sample, we have almost a probability of 1 because we've seen everything in the sample. And if we don't have very many elements, then we have a low probability, and we accumulate them as we move from small to largest, at least in the usual way of structuring it. And in this case, somebody's passed a blue curve through the red dots, but that's irrelevant. Okay, any other questions before we move on? Okay, cool. Those were excellent questions. Let's look at a practice exam. So this is a practice worksheet adapted from an older exam. And right here I have an unusual thing. I'm going to reset everything. God, I hope I don't regret that. And so this is running on, this is my home computer. And on your exam, you'll have a block similar to this. Be sure to run that block first and then go ahead and take your exam. If it creates a pink box of error, don't worry about it. Move on. Leave the pink box of error there. All we're interested in is that you run this cell and you get a whopping 1 point for that. So that's the easiest point you'll ever get in the history of the world. So here's an example problem. Let's suppose we have this table which contains some experimental observations, and we're instructed to, 1, plot the speed versus time, speed on the y-axis, time on the x-axis, using scatter plot, and use blue markers. Our second instruction is to plot a red line on the scatter plot based on the linear model f of x equals mx plus b. Our third instruction is to, using trial and error, find values of m and b that make our red line fit our blue markers. And then our last instruction is, using the data model, which we have just parameterized, make an estimate of the speed at time equals 15 seconds. So this is just like a lab assignment and a lesson assignment. So whoever created this even gave us our instruction set right here in these code boxes. So the first thing we need to do is create the 2 lists. So I'll do the hard work, and since it's a workshop, you're going to tell me what to do on the easy stuff. We'll create a list called TOBS for observed time equals, and speed OBS equals. Now I have those as empty list. What goes in time OBS? Oh, everybody got.
Should be the elapsed time.
0
Correct.
through 10.
No?
Okay, 0 through 10, we'll do it the lazy person's way. And there's no critique on that. Lazy is not necessarily wrong. And let me drop a decimal point on the last one. That will make my list. It should force it to float. And now for the speed, OBS. If somebody says the second column labeled speed in meters per second, that would be good enough. So somebody say that.
The second column.
Very good. Okay, so 0, 3, the other 3, 7, 12, 20, 30, 45.6, 6, 0.3, 7, 7.7, 9, 7.3, 121.1. So there are our two lists, time and speed. So we've entered them, and we can, how would we verify that we actually got values in either of these lists?
You could print
And
both.
Okay, I like that. That was actually more complex than what I was going to do, but we're going to go with that.
What's the other way?
I was just going to actually write the variable name and then run the cell, and it has the equivalent of printing, but you can only do one at a time. This way we'll get both. And we could try to print them side by side in columns, but all we're really trying to do is verify that we actually built them, and that looks good. Then we will suppress the printed output because we don't really need it. All right, so we've done our first part, which is to get the data into our worksheet. And in this particular one, the next step was to create the data model function and then make the scatter plot. So let's go ahead and follow that instruction. How do we make a data model function? How do we make any function? It's a 3-character
define it.
Define.
DEF. What do I put next?
The name.
The name.
Name,
of the-
okay. What else? What goes next?
Like the variables or arguments, I think they're called.
Okay. So we're going to have a function. I don't actually like that name. We're going to have a function called fn, and it's going to take 3 inputs, an x value, an m value, and a b value. And what is fn going to do for us? Fn is going to take m times x plus b and send it back to us. Spelling counts. We're not doing any error checking, so bear in mind it's quite possible to supply values to the function that break it, and we won't get, we're not doing any error checking. If we were doing this professionally, in the sense being that we would hand it off to colleagues wherever we're working and they'd have to use it a lot, then we would be obligated as the engineer programmers to put in all the error checks that we can imagine to prevent it from breaking something else. Basically, our own pink screen of death. Okay, so now it says create a model list. Let's go ahead and supply a value for m. Do a slope of 0, and dang it, my editor's not working the way my brain thinks it should. An intercept of 0. And now we have time mod. So we want to make a model time, and that's going to be a list. And let me see if I can pull this off. I for I in range 0 through 10. I think if I do that, So this is a programming trick, which may or may not work. So that's called a constructor notation for building lists on the fly and populating them. I'm not sure if I have the syntax quite right, and there's one way to find out, which is
Google.
that Google's what I'm going to do if I can't make it work. What do I do next just to see if I did it right or not?
Oh, first you run it.
Very good. No complaints there. So let's go ahead and print it. And it's not subtle that I made I into a float. That's kind of important because in order to be comparable, we need it to be a float. So I want to get the 11 here, and because I want to get 10 inclusive, I do that. Beautiful. I now have my time model. Next thing I want to do is create a speed model. I'll make that an empty list. And for I in range to 11, do what? SPEED underscore MOD dot APPEND. And what do we want to append? We want to append FN of time underscore mod index I, comma M, comma B. So I'm using the append feature of lists, and I'm going to put into the list speed underscore mod the result of the function fn for each value of time underscore mod. And again, to find out if I've made a syntax error, what would I do?
Run.
Run it and hope for the best. And that is actually pretty cool. So now let's go grab our print functions and check that we have something. Now, I'm quite aware that a value of m equals 0 and b equals 0 isn't going to be close to my observed. That's not a problem yet. Change that to mod. Change this to mod. Unsuppress, unsuppress. Okay. Let's change my slope to 1, so at least I'm basically with the slope set, with m set to 1 and b set to 0, our function is the return function. It's going to return the values of x. And sure enough, it does. Okay, so we're good. We now have a list called time OBS, speed OBS, and another list called time MOD and speed MOD. Which represent our observed and our modeled values for time versus speed. So now we can consider making plots. And fortunately, in lesson 14, I think we did that early in the lesson. And the reason this is important is I actually want to go steal my make2plot script. So here what we're doing is the best kind of CCMR. We're going to make our own plotting function. So I'll copy that, go back to my workspace. So I'll import my matplot library, and then I define my make2plot list1, x1, y1, x2, y2. It looks like it's in the right structure. Let's go ahead and mess with the sizing. Let's just make it an 8 by 8, and then we can jack with the size later. So our list 1, we're told to use blue markers. And red for the line. And I'm using a matplot library trick here that we've done in lab and in class. By setting the line width equal to 0, I'm going to make my marker a P. That's going to plot blue points when I access this plotting function. And let me make my legend have meaningful values. Our first series are observations, and our second series are going to be our model. So we run that without protest, and now we can go ahead and consider making our plot. And in this case, we want to make two plots. It says create a scatter plot of time and speed, overlay time and model speed. Got it. Make two plot. So our first list is our observations. So time underscore OBS comma speed underscore OBS, time underscore model, speed underscore model. And I'm quite aware that I could just reuse time. It should be the same. And next thing, we need our label X is a string. So what do you want to label the X-axis? You want to label it elapsed time. No, this notebook with practice problems is not available. Just watch it and pay attention. In seconds. And what do you want to label the y-axis? Anybody?
Time, or
Let's call it speed, my favorite movie. Meters per second. And let's see, we need a plot title. My plot. Okay, so this should generate the plot. We've already done all the hard work back in lesson 14. There is no logical reason for you to repeat hard work. So by all means, what if we had 0 to 100 for time? We'll get to that in a minute after we get this one done. And then the question is, the notebook with the practice problem is going to be available. I'm not going to put the notebook as a Python notebook, but I will, when I'm done with the workshop, I'll go ahead and render it as an HTML. I'll put that up on the web server. And the reason being, this is running on my home Raspberry Pi, and moving crap around is a real pain in the neck. Okay, so let's get on with that. So how do I find out if I've made a syntax mistake or not?
Run.
Run it.
Sweet. So there is my observations as, well, that's funny. I didn't know that a P made that particular marker. My blue markers, and there's my red line. And our first inclination is that's a really terrible fit. So let's see what it tells us to do. So we've done the red line. We basically have satisfied exercise question part 2. By trial and error, find values of M and B that make a decent fit. Okay, so M changes the slope. It's going to tilt that red line up and down. So do you think M should be bigger or smaller?
bigger.
Okay, so I got a bigger, how many biggers?
Bigger.
Got 3 verbal biggers and about 2 of them in the deal. So I would agree with you. Bigger is good. Let's go with 5. We're getting better. I would think bigger still. I'm just going to pick a number.
Maybe 15.
There's 8. So we could stop there. Our next thing is to consider messing with the intercept. We could maybe make this -5 and play with it. So that's, anyway, that's what you're to do. So let's, for the sake of getting on, we're going to declare that that is a best fit we can possibly get. Or we could go crazy and try that one, replot it. And that's terrible, but if I actually jack the intercept down quite a bit, watch what happens. I'll end up matching the later part. Not too good. So that 16 was too much slope, so let's go down to 12. Okay, I like that. We'll stop there. Report the best values of M. This is where you would say, my best guess of M is
12.
I'm just going to actually report it back. Why try to read when the computer can read for me? Yeah, I think you're right. I think it is 12. I'll go ahead and give myself. So my best guess of M is 12. My best guess of B is minus 15. The last one, it asks us to estimate the speed. So we will print estimated speed at time equal, and we want to do it at 15 seconds is Fn. What do we put for our X value? Need an X value.
15.
15 it is. Done. That's based on our model, so it's projecting it out to 165. Now, if we chose a different model, so just looking at this, what do those blue dots look like to you?
Parabola.
Yeah, it looks parabolic. There's definitely curvature there, and a straight line can't pick up the curvature. And so we could modify our function to incorporate curvature, but we won't do that. That's for another time. There was a question, what if you wanted to plot the 0 to 100 for time? This is what I think I would do. So this is going to dramatically change the appearance of our plot, not necessarily for the better. And hopefully it did that right. Ooh, it got pissed at me. What's the error? X and Y must have the same first dimension. So my X2 list, I got the time. Probably should make that a variable. There is what happens if we make our X and Y, our model go between 0 and 100. So in that case, our fit looks really good because all the observations are smushed down here in the bottom. But what I suspected you probably meant was, what if you wanted to do stuff to 100, but in steps of a tenth, for instance? We simply add the step counter in. I think it needs to go 0 to 101 in steps of, well, we'll find out. Float object cannot be interpreted as an integer. Okay. But I know what I can do. I can certainly divide that by Actually got a no math. So there, oh, that was not what I wanted. Maybe I need to multiply that. So now each of my increments is 1/100th. And anyway, that's how you do bigger ranges. But let me put it back to the way it's supposed to be for when I render it as a HTML file. 11, 11, move on to the next one. There we go. Okay, so questions on that? Good. Let's go to, as you know, Farang and myself love to play Russian roulette on the computer, namely because you can do it without getting a hole in your head, or spare hole. I mean, you've got 5, or 7, I guess, if you count your eyes, 7 to begin with, but no extra holes. So let's read the problem. It says, consider the script below, and this is actually fairly typical, very typical what you'll have to do. You're going to use a lot of other people's scripts, and we're testing you on this exam, the ability to use another script, figure out what it's doing enough to be able to use it. So consider the script below, which crudely implements a Russian roulette simulation. How many times can you spin the cylinder and pull the trigger before you fail? It says play the game 10 times and record how many times you can pull the trigger until you fail. It'll say bang, you're dead. So it says create a list of pulls into failure for each of your 10 attempts, and then make a histogram of that list. And then from the histogram, estimate the mean number of pulls to failure. The second part says in the movie The Deer Hunter, and there's a link to the movie, captured soldiers modify the game by using more than a single cartridge. So you're asked to modify the program to the number of cartridges in the movie and play it again 10 times, record your pulls to failure, make a second histogram of the Deer Hunter version of the game. From the histogram, estimate the mean number of pulls to failure under the Deer Hunter conditions. And it wouldn't take a genius to figure out that for an exam question, there might be a few more questions like, do the two things come from the same underlying distribution or not? And that would be a hypothesis test. But first, let's figure out if the program even works. So here's a bunch of Python gibberish. As far as we're concerned, it's just green, red, and purple things on the screen. So, okay, this is it's the interactive part saying this is a Russian roulette program, best played while drinking vodka. Press enter to spin the cylinder and test your courage. So I'm going to press enter, and I pulled it once, and it went click. So if I press enter again, I'm going to spin the cylinder and then click again. I pulled it twice. I'm a lucky person. Spin it again. 3 times.
That's very lucky.
4 times. I wonder if I've already modified it. Oh, darn it. I pulled it 5 times. Bang. So long, comrade. So I got, in my first game, I made 5 pulls to failure. But since failure is not permanent, let's go ahead and play it again and see what happens. 2. Oh, I got 6 pulls that time, which makes sense. If he only has 6 cylinders, you would expect by the 6th one to be croaked. So my second one was 6. Let me play it again. Okay, so I played it 3 times interactive, and now I think the way the game works is there is a variable called trigger pulls, which keeps track of the number of times that I pull the trigger until game over. So what I want to do is every time I play the game, I want to capture the number of trigger pulls. So I am going to wrap this thing into a function. And I don't really need variables. Well, actually, I'm going to be lazy. The way I would do this on an exam, I'm going to go ahead and create my own list. Pulls to die equals empty list. And I'll go ahead and just play the game interactive real fast. 1, 2, 3. Okay, so my first one was 3 because we're told to play the game 10 times. 10 times is small enough that you can do it manually. If we want to do it 10,000 times, we would want to wrap it into a function. Ooh, 3 again. I'm not getting my 4.
Why was there 4 this time? Oh, I see what we're doing.
Yeah, it's a random number generator, so. Oh. I'm really lucky. Oh, I may have broken the program. There's no way I should get to play it 10 times. Yeah, something's broken. It shouldn't. 16 pulls. We're going to keep that. That's the way I like to play Russian roulette, especially when there's 14 other people playing with you, because you end up getting to take all the money and the vodka. Seven. So I need to play it 6 more times. And you can see why in the simulation part of the class, we would program it to play the game for us. Because in the movie War Games, you could see how much easier it was when you had the Whopper playing the game for you. 1, 2, 3, 4, 5, 6, 7. Got to play it 3 more times. That wasn't very successful. 2. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9. One more play. That seems appropriate for the last one. Okay, so there's a list of my results. Now, how do we make a histogram? I don't know how. But I bet I'm going to need matplotlib. Let me go back to Scheiße. Lesson 14, see if there's anything there. Okay, matplotlib, blah, 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 histograms. Nope, so I think the histograms are probably in lab 14. Oh, there's a histogram there, how convenient. Let's see how that was built. Looks like that histogram is using NumPy, but it looks like it gives us enough to get the syntax for a histogram. Okay, so now I got to go look up the syntax for a histogram. So now here I'm using my friend Google, and I love the thing where it says example. So we'll go with an example. Let's see, matplotlib.org. I would suggest avoiding that because it will probably be too much. Let's look at tutorialspoint.com, Stack Abuse. I like the name. W3 Schools, a personal favorite. RealPython.com, Stack Overflow. We are going to try tutorials first. Okay, so looks like the plot call is plot.histogram. I think we have all we need. So let's look at our thing back here and see how we built plots. If we keep that, it tells us that plot.hist is what we're going to want to use. So let's see if that will work. We don't need to import that because it's already there. So plot.hist, and we tell it what to plot, puls2die. And make sure I'm not, let's see what happens. Name plot is not defined. Of course it's not. PLT. Pulls to die is not defined. There's my histogram. So create a list of polls until failure for each of our 10 attempts. Done. Make a histogram of the list. Done. From the histogram, estimate the mean number of polls to failure. So somebody make an estimate of the mean number of polls to failure. On average,
I'd say 6 or maybe 5. I'd say 5.
so the 4 to 5 bin, so the mean number of polls to failure is roughly going to be where this pseudo distribution looks like it might balance. So you claim 5, that's fine with me. Print so there's my visual estimate, but what if I wanted to do a little bit better quantification of that? Is there any
We could
ideas?
use describe.
Pardon?
We could use describe.
We could, but this is not a data frame. So
Could we turn it into a data frame and then use describe?
we could, or I think there is a formula called maybe sum.
Or
believe-
could we use the mean?
I believe there is a built-in formula called sum. There is. Divide it by 10. Copy that. Paste it there. The visual estimate is 5. Sample estimate is run it, and it failed to take my input because it's a piece of crap. There we go. Visual mean estimate is 5. Sample estimate is 4.6. Okay, Deer Hunter version. How do we modify this for Deer Hunter? Since I don't think it's a good idea to break perfectly good working code, I'm going to grab that cell, copy it, paste it, and we'll make this is a deer version of Russian roulette. Best drink while drinking nasty Mekong river water, because that's what they were doing in the movie. Okay. So what do we have to change in this script to make this behave the deer hunter way? Let's take a look at the script now, this time in detail. So we have a while loop, which it runs repeatedly until we enter the leave program input, which is the literal Q. Excuse me for a moment. Frank, can you take over?
Yes. So, any
Hello?
questions?
Hey Ted, this is Ken. Can I borrow you for a question?
Dr. Cleveland, we can hear you.
Just a second. Let me turn off my.
Okay. So, seems like you're stuck with me, guys. Is there any questions that you want to ask me? Not necessarily related to the notebook that Dr. Cleveland is covering? No?
Well, what's a good barbecue place?
Are you still in Lubbock?
Yeah,
Have you tried Heavy Maze?
where's that?
What? You haven't tried Heavy Maze yet?
I haven't, like, I'm bouncing in and out of Lubbock, so.
Okay, so it's like a 10-minute drive. It's in Walforth, and if you just use your Google map and go for Heavy May, it will take it to you.
Okay.
And I suggest going very early. Try to be there around 11, because there usually is a very huge line.
So I guess I can't get it after the exam then.
No, that will probably be too late, even though it's a Tuesday. So if you want to do that, give them a call and ask if they have enough food.
Okay.
And when you got there, my recommendation would be the burnt ends, regular brisket if you're interested, and some ribs. Definitely give those a try. They also have good sausage. If you are going with a party, you can also give the beef ribs a try. They're huge, but very tasty.
I have to give that a shot.
Yeah.
But my other question is for the cumulative, what is it, the
CDF.
CDF? So is that the one where, like, is that the one where it's, you have this chance of something of this magnitude or lower happening?
Do you remember when we were talking about me going to the river and taking samples?
Yes.
Okay, then I told you that, okay, I have a bunch of samples, let's say 100 points.
Yes.
And then we wanted to get this plot where it had all these points on it. And looking at those points, we could say, okay, what is the exceedance probability associated with a flow rate of 100 CFS? What is the exceedance probability associated with a flow rate of 40 CFS? Do you remember that?
Yes.
That was the CDF.
Okay.
For us to plot our samples on that kind of CDF and on that kind of plot, we need to use a plotting position formula, which Weibull is one of them. So you first sort your samples from small to large, and then based on the rank of the sample in each set, you get the values for the Weibull plotting position, and then you plot it. You will get those points in the certain order.
So it's the actual graph, not necessarily the That
The CDF is the graph,
okay, yeah. Okay.
but the plotting position allows you to take your samples from raw numbers
And
to
extrapolate.
ranked points that you can plot on that graph. Abby, is everything all right?
Yeah, what? Yeah.
Because you're not eating.
Oh, I already ate.
Oh, okay. I didn't see
And I ate wings again.
that.
But I am eating dark chocolate though.
How dark?
Wait, what?
How dark? Like, what is the percentage?
Mm, doesn't say. It just says special dark.
It's weird.
Mm,
I used to have a teacher at school. He was diabetic, and he used to eat 95% dark chocolate, I guess, because supposedly it will make you not feel hungry. It's so bitter that you prefer not to eat anything.
no, I just like it because it helps with my mood swings.
There's a really good dark chocolate. It has like the orange like pieces in it. That one you should give a try.
Is it really bitter, or it's around 60-70%?
I think it's around 60 or 70%. It has like little like chunks of orange.
Awesome.
Like so yeah, that one's really good. My boss got it one time for us and I was pleasantly surprised.
Yeah, 70% is the maximum that I can go to. Above that, it's not chocolate anymore. It's really amazing that as soon as Dr. Cleveland walked out of the lecture, you all start talking about food with me.
Okay,
so
I'm
food
back.
with me, technical with Dr. Cleveland. I will send it back to you, sir.
Okay,
You are
I just
the
took the host
now.
back. I was doing technical support for EPA Net. So, okay. At this point, I was trying to figure out what this program does. So all you guys did was talk about food?
Pretty much, yes.
Okay. So as we're working through this other person's program, we have this thing where it says number equals random.randint 1 through 6. So we already know what that does, right?
Yes.
Yes. What's it do?
It makes
Yeah, more positive than number. It chooses an integer between 1 and 6 inclusive at random. So sometimes it'll pull up a 1, sometimes it'll pull up a 3, sometimes it'll pull up a 2. Heck, we could use this in Las Vegas to program a video dice machine. Okay, so that's pulling a random number. And then it's testing. If the number is equal to 1, what happens?
Nothing.
You don't die.
You don't die. Okay, yeah. Something happens. It prints click. It increments the trigger pull counter. It tells us how many times we've pulled the trigger, and then it gives us the opportunity to leave the program. If it comes up a 2 in the random number generator, same thing. Click, trigger pull increment, trigger pull list. Do you want to leave the program? If it comes up 3, click, pulls, leave the program. Comes up 4, click, pulls, program. Comes up 5, bang, you're dead. So long, comrade. Tells you how many times you pulled the trigger before your brains are leaking out of the hole in your head. And then it sets the leave program value to the literal Q, which actually is what triggers bad word choice there, leaving the program. And then if it comes up 6, trigger pulls increment, click, and continues. So to make this to the Deer Hunter version of the game, which is 3 cartridges instead of the usual 1, what we need to do is make 2 more of these numbers behave like number 5. So somebody pick your favorite number of the alphabet between 1 and 6, not including 5, and we'll change that to behave as a second cartridge in the bullet launcher.
2.
2 it is. Okay, so we're going to have to do some very difficult programming here. Watch this closely. Copy, paste, save it, and now we got to make one more cylinder behave badly. So
4.
4 it is. Okay, so now we have 3 chances in 6 of splattering our brains over the little bamboo cage in the jungle in the movie, and 3 chances out of 6 of walking away. Now, if you watch the movie, you'll see that the character played by Robert De Niro plays a rather sneaky trick on his captors. And of course, since he's the hero, we're happy that he does it. Anyway. If you have time, watch the movie. It'll make this test easier for you to take. Not really. So we've modified the program. Let's see how badly we've broken it. Okay, this is a Deer Hunter version of Russian roulette. Best played while drinking nasty Mekong River water. Press enter to spin and test our courage. Oh, we're goners. However, we need to keep the list of the result. This is Deer Hunter pulls to die equals, and again we can do this manually. So we did 1 pull and we're dead. Let's play the game again. Wow, 1 pull and we're dead. Make sure I didn't screw up when I did the cut and paste. Bang. Yep, that's play it again. Oh, 2 pulls and we're dead. Out of luck, last thing. LMA, Lamau. Yeah, this is a hard game to win at.
At least it'll be easy to see the distribution, the mean.
Yeah, should be a little easier. Oh, we got by once. We already know what's happening next time I pull the trigger, right? Yeah. 2. Oh, not bad. I made it 4 times that time. That would be, I have a good script writer. 1, 2, 3, 4, 5, 6, 7, 8. 2 more plays. One more play. So there's my 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now we want to plot a histogram. And as good data scientists, what we don't want to do is actual work. So we will just copy and paste and then change the name. That histogram look any different?
Yes.
That'd be a yes. And actually, if we did some reading, we could plot both of them on the same axis. We did that in lab 14. Let's see if there's any. If I generate a plot figure and just blast the 2, bet I can get them on top of each other. We'll try that in a second. That's less crucial than figuring out our poles to failure. Again, copy paste. Played it 10 times. Okay, so our sample estimate of poles to failure in the deer hunter case is 1.8, where our sample estimate of poles to failure using conventional Russian roulette is 4.6. And there's a lot of interesting ways you could modify this game. We could use a 8-cylinder revolver, a 20-cylinder revolver. A D20s are a Farang favorite. I'm not aware of any 20-cylinder revolvers in existence today. Undoubtedly, they have been built in the 19th century. And we can explore a few seconds of attempting to generate 2 plots on top of each other. So let's copy some of this part right here, and then we'll modify it to fit our case. So we generate a figure. Make my histograms, and is our plot called plot? It is. So there's our figure. We want to copy that. We'll paste it right there, and we'll see if we actually get color equals red. And then we'll copy our other histogram. We'll leave it alone. Copy that. Put that right here. Put that right here. Actually, I think those need to be indented. So let me tab those, and PLT SHOW. So I don't know if this is going to work because I'm just hacking in the plotting thing. This is the kind of stuff that as you were doing your labs and homeworks, you probably built your own plot functions. By all means, use them. Unexpected indent. And the error is rectangle has no property. That's bizarre. Oh, color. There we go. So there are our 2 histograms right there. So plotted on the same axis, and from that it should be quite obvious that the deer hunter version in red is quite a bit different than the conventional version in blue. If you don't like blue, we could always pick another color. Let's pick green. So we got the red-green show. Okay, any questions before I move on? Abby has told me that I'm out of luck, which is indeed true. Next one is, well, let's read it and see if we can figure out what to do. The data below are the impact strength of packing materials in foot-pounds of 2 brands of boxes. Produce a histogram of the 2 series. Determine if there's evidence of a difference in mean strength between the 2 brands. Use an appropriate hypothesis test to support your assertion at a level of significance of alpha equals 0.10. So we have United States Postal Service boxes, and we have a list of strengths for them. And we have DHL boxes, and we have a list of strengths for DHL. And our first step is to produce the lists and make them into a data frame. So I'll first write the lists, USPS equals a list. DHL equals a list. And then we want to make it into a data frame. So what should go into the lists first?
The values.
The values. Excellent. What would be the first one in USPS?
1.25.
Very good. I'll do the rest. I won't keep asking you that. Okay, and then for DHL, obviously, well, maybe not obviously, it should be the next column. And while I'm doing that, one of you of the more genius type, or maybe the non-genius might be better at it, go ahead and look back and find out how to take these two lists and put them into a data frame. 0.94. 1.01, 0.97, 1.05, 0.97. So there's our two lists. Go ahead and enter them. And then to be sure that we got the data in, we'll do what we did on the first problem. We'll just go ahead and print the lists. Again, because it's easier to cut and paste than it is to actually think and type, we will cut and paste. And USPS, DHL. Okay, that looks good. So did anybody figure out how to put two lists into a data frame? Well, going by the deafening silence, I'm going to assume no.
Can you do df or whatever you want to name the data frame is equal to pd.dataframe and then parentheses bracket and then you do the name equal to the data?
Okay, I think you're on the right track, but we have to do something even before that. You need to import pandas.
Import pandas.
And let's go back to the data frame lesson, which was right here, lesson 7. And let's see how to build data frame. Oh, we actually can use our original example from the lesson. We can also turn our table into a data frame. Notice how the constructor adds a row to get proper behavior. So we want to do something like that. Let me get to my Jupyter lab. So let's call it my data frame. Actually, my data is enough. And we have to tell it okay, row name, tabular. Let's just see what happens because our actually, let's get smart and use pandas dataframe from twolists. How to create pandas data frame from multiple lists. So again, using our friend the Googlebot, let's say we have two lists. One approach is from one or more lists is to create a dictionary first. I don't like that. So let's keep reading down. Second way to make data frames from lists is to use the zip function. Ooh, that looks cool. So we get a data frame, Panda data frame, data tuples. Let's try the zip function. I've never done that. That's pretty cool. So we're all zipping together today. Use Python 2 is enough. Okay, so in Python 3, list zip what? Okay, so let me make my zip equals and USPS comma DHL. Now we run it, see if we get, oh, that actually worked. Huh, that's a first. Go back to our website. Since we're actually literally copying someone else's work, we want to CCMR this. So there I've left the website how to do it. And now that I've zipped it, next thing is make a data frame from the zip, and then you can name the columns. Okay, we'll do that. IP, so you make it from the zip, and then columns equals, and then you give it the keys. So our first key will be USPS, and our second key will be DHL. With any luck, my data, ooh, so far still didn't protest. Let's suppress the output because we don't need that anymore. How do we tell if my data is the data frame that we want? Oh, somebody suggested in the chat box. Cool. How do we tell my data is or is not a data frame, or what it looks like?
Couldn't you print it or just retype it, just my data?
That's one way. Can you think of any other methods that are conferred to us by the fact that it's now a data frame? Perhaps the head, and it gives us the first 5 rows, USPS, DHL, and indeed it looks like it's supposed to. We could describe it, although I think we actually have to do that later on. Okay, so each of them has 9 things. The mean value for Postal Service is 123, DHL is 0.96, standard deviations, min, max, range, and so forth. So describe the list or data frame. Let's go ahead and do that. That was an easy point right there. Done. Now we want to generate histograms. Remember how to do that? I think we can do that from lab 14 because we did those as data frames. I think we can use this structure here from our lab 14. So we'll keep that and we will try to transfer that knowledge here. So we want to generate a histogram of USPS and then a histogram of the other one. So data plot. Nope. I'm going to cheat. Histogram. we're in pandas, right? So I want histogram from data frames, pandas data frame hist. Okay, pydata.org. Those are going to be unreadable references. Creating histograms using pandas. I like this. A guided walkthrough on how to create a histogram. That sounds pretty fun. And more importantly, easy and likely to have code that we can cut and paste directly. Data visualization. We will use pandas hist method. And so data frame and then hist. There is the syntax right there. We already have our data frames, and we go back to our workbook. So first we got to use my data, and I want to get a histogram of USPS. I hope this actually works. I'm not sure I'm getting the key correct. Oh, well, that did work. And if we want to make the histogram of the other brand, what do we do? Anybody? I know I'm still out of luck. Okay, well, so to get the histogram of the other variable, we type DHL because that's what we named that. And there is USPS and DHL. And up here, we saw how to get two histograms on the same axis. And there's an example in lab 14 that does the same thing. You're on your own to figure that out. So now we want to run some hypothesis tests and determine if the mean values are the same. Let's return to lesson 14. And did we check if the means are the same? Why don't we first check Mayday? Oh, that was weird. Well, I would propose that we check for normality because it would be nice if we're testing for the means being the same. If we know that the underlying distribution is Gaussian, that lets us use what kind of hypothesis test?
Parameterized.
Yeah, a parametric. Okay, so our data is called my data. Our first key is USPS, and I'll leave the p-value as is. And that was wonderful. It says it was probably Gaussian. So now let's, again, copy and paste everything. We'll now do it on DHL. DHL is also Gaussian, so that's very, very nice, because that means, according to our lab 14, since they're probably Gaussian, we could use Mann-Whitney, or let's see, Mann-Whitney is non-parametric. Let's find a parametric test. Parametric. Dagnammit, that's got to be lab 15. Well, we'll run the Mann-Whitney while we're here because I can copy and paste it. And my data DHL, copy that, goes there. And my data USPUS, copy that. Goes there. Okay, so this is telling us that those two distributions are probably different. And what we really want to test is the difference in means. So our test statistic would be the mean value of the first one I think mean is a built-in method. One way to find out will be to run it. We already know they're different when we describe them. And then we'll take the difference. Minus DHL. And if we DIFFMEAN, says the difference in means is 0.26. If they were the same distribution, we'd expect the difference in mean to be close to 0. Let's go to our lesson 15, which I think was the next lesson after 14. I can count. And that should have a hypothesis test. It does, and I want to use a parametric one. We already know that we can because we've already tested for normality. We go past the pregnant doctor, and okay, normality, parametric, student T. The means of the samples are equal. The means of the samples are different. That looks like the test we want to use. Is that what you all think? Is there anybody out there?
I mean, looks like it should work.
That looks like a good choice for me. Again, using the miracle of cut and paste. Let me suppress this output. So we certainly don't want this garbage in the way. I hope I have Skippy stats on my local machine. That we'll find out real quickly. So my first entity is the Postal Service. My second entity is DHL. And let me modify my report, MEANS. Okay, and then we would interpret the findings. So the means are different, and look at the attained probability in the case of the means. If you remember that the attained probability, the p-value represents the probability of the area between the overlap of the two distributions is 0. These distributions are pretty far apart, and that would be the interpret.
So
All right.
I have a question.
Okay.
How do we know which test to use? Will it be given, or is it just kind of, if you find something on the internet, go for it? Or
Well, let's consider the number of tests that you've been shown. You've been shown tests for normality and tests for differences in means. So that is your universe from which to choose. And you have non-parametric tests for when they're not normal. If you go on the internet, you're going to come up with the same things as we've shown you, because there are no particularly magic tests out there, even in the dark web. the Vladimir Putin test still is a t-test. So that will be the test that you use. So we tested for normality. Once they were normal, that allows us to use the student's t-test. And the student's t, according to our lesson 15, the null hypothesis, means are equal. The alternative, means are not equal. We could do paired student t. It's basically testing the same thing. We could apply an analysis of variance, but that makes no sense in this instance because we only have two things to compare. So based on what's been presented in the lesson, those are your only choices. But if you go to the internet and find a harder way to do it, by all means, document that. Any other questions? That may not have been the answer that you wanted to hear, but pretty much you don't have very many tests from which to choose. Follow the logic that's presented in the lessons in the laboratory and you'll be fine. All right, it's 6:30. The last example, I actually left some notes to myself ahead of time. So this one is getting on to where we're going to build a data model and use our Weibull plotting formula and all that. So this one is evaporation records for Texas are available from the Water Development Board, blah, blah, blah. Cell 911, that's the one that we want to work with, which is actually down here. Copy of the data set downloaded from the Texas Water Development Board is located at, and if you have a question like this on your exam, a correct URL will be provided. Produce a plot of month versus precipitation. So what we would have to do is import pandas, read the file, and I've already set it up. I'm going to name my data frame evap.df. So the first thing this test is, do you remember how to read an input data file? And in this case, we have to parse based on dates. So read the file and assign to a data frame and then display the first few lines. So let me run that. Oh, good, it worked. So there's my data frame. This column is years and months, and then we have these different column headings that correspond to cells on this map, and we're interested in cell number 911. Second step, describe the entire data set. Produce a plot of month. Let's go ahead and make the plot. So we're going to use, in the pandas, there's a line plot function that's available. We're going to make the x-axis year, 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 month, month. Y-axis will be the contents of cell 911. And we'll plot that. There's our plot. So we have these evaporation rates in inches per month over the 60-year period. And then describe the data. There's 792 records, has a mean value for standard deviation of 1, minimum 1.23. So there are no months in over 60 years of zero evaporation, maximum of 9 inches, median of 4 inches. So on average, evaporation in cell 911 in Texas is 4 inches. It's never been observed to be larger than 10. It's never been observed to be smaller than 1.23. Okay, produce a plot, describe the data set, split the data into two parts. This is where we use in pandas our conditional selection tools. So back in lesson number 8, we're going to have one called evaporation before 1985. And there's the filter. It's going to take evaporation data frame, and it's going to select values of 1985-04 or smaller, and it's going to create that into a new data frame called EV B84 B485 lock. And then to simplify our work, those location values are going to be indices. We'll go ahead back to the original data frame. We'll pull out just those locations and we'll put them into a data frame named EV B485. We'll repeat the same for after 1985. We will go ahead and prepare a subset, and we'll look at the heads of the two data frames we've just created. So here's the first series from 1954. Here's the second series. There's the second series from 1985 onward. And now we will describe the split series for cell 911. So before 1985, we run that describe. Afterwards, we run that one. We see that prior to 1985, there's 375 entries. Afterwards, 417. So these are not the same size, but they're close. The largest evaporation in cell 911 observed before 1985 was 8.8 inches, and the smallest was 1.26. After 1985, the largest evaporation observed was 9.56 inches, and the smallest was 1.23. So on the largest end, there's almost an inch more of evaporation observed in the latter years. And our next thing is to plot the split series. And I don't have that done ahead of time. We would essentially use that plotting function, but on different data frames. So let's go ahead and copy and paste those. Okay, so I want to, what do I want to plot? I want to plot EV B485 and EV85 up. Let's see what those two plots, and we want that to be, I hope this works, COLOR equals quote. I'm going to COLOR equals quote. And with a little work, I'll leave you to read on your own. You could put them on this on the same. Actually, no, you can't put them on the same axis. But you can actually make it a single plot where it switches from blue to green when you cross over. So we've done the plots, and looking at the plots, I mean, they're different because one's blue and the other one's green. But the more recent ones, they look awful lot alike. Compare the sample means. Now, how would we do that? I'll grab the two data frame names. How do I get the sample mean of each one?
Describe.
Well, watch what happens. Remember, we're interested in cell number 911. We'll just do one of them. So if we just wantonly use describe, we're now getting it for every single cell. We want it for a particular cell. We want cell 911, so we have to identify the key. Okay, that indeed gives us a sample mean, so let's go ahead and do the same up here. And we get the lovely problem that it only shows the last thing. So we'd actually have to print these. Get that one wrapped in the print too. All right, so compare the sample means. How do we compare sample means? Oh, let me scroll up a little bit.
Can we use those tests,
Oh, excellent, thank you.
the t-tests?
Yeah, we've already done work on sample means, so let's go ahead and just test for normality first. So all I'm doing is copying that, get back to where we're described the sample means, paste that, and now I need to EVB for 85 key 911. Let's find out if that one's normal or not. Of course, it's not Gaussian. Let's check the other one. And this is 85 up. Both not Gaussian. Oh, so I guess we quit. We can't do any tests, right? Non-parametric hypothesis tests. We can look at Wilcox or Kruskal-Wallis. These are for testing distribution versus distribution. We want to just see if the sample means are the same. We can still use a t-test. It's just not going, the p-value will be incorrect. I'll go ahead and use a t-test knowing that, because we've already got the script written. Or we could apply Mann-Whitney. We'll do Mann-Whitney. Because even though it's reporting maybe the same distribution, maybe not, it's really testing the means. If you read about the Mann-Whitney, we'll find that. So let's go ahead and put our guys there. Probably the same means. Okay, so the Mann-Whitney non-parametric test suggests that the mean value are the same. Let's go ahead and apply a t-test incorrectly, but we can apply it anyway. The computer doesn't care. And if we apply the t-test to data that are not well described by a normal distribution, the consequence of that is that the computed p-value at rejection is meaningless. It's wrong, which doesn't mean that the test is a complete waste. But if we're close to our rejection region, we would be concerned. And in that case, the means are the same. So we would conclude that it's probably got the same mean value. Next thing we're instructed to do is to create a Weibull plotting position function. We can copy that from our lab. If I can remember which lab we did it in. Wasn't lab 14, so maybe it was lab 15. No, it's got to be earlier. I don't think it's in lesson 15. Nope. 14 is plotting positions. Okay, probability estimation, norm density, Weibull. There's a Weibull function right there. So that's got all the information we need to know. Weibull plotting position function. Let's go ahead and make it as a function. DEF Weibull PP, and it needs a list. RETURN. See if that's going to work before I even try it. So it's Actually, I'm not going to do it as a function. We'll just do it raw like that. So there's what we need to do. What we need to do first is to sort. We're going to need it for before 85 and for after 85. So let's make it work for one, and you can do the other one on your own. So EV before 85 key 911 end key. Sort it, and let's put it into before list. Let's get my spelling right. So now I have a list called before list. And let's see what happens. Ooh, I hated that. Series object has no attributes. Sort. Of course it doesn't. I'm trying to avoid looking at my series object has no attribute sort. I wonder if it works like that. As list. So that as list function is not part of the data frame. Let's go see how I've done it before. Well, what we could do, are we stuck or not? Want to see if we can prevent Farang from dying? Our Weibull plotting position, we made it to work on a list. And we need to turn EV before 85, 911 into a list. So let's go to our friends here. And we got 9 minutes to go, and then I'm done. Pandas, data frame, to a list. Okay, get list from pandas data frame. There it is. Okay. So we use the data frame key, and then we have the to-list functions. I was close, I just wasn't typing it quite right. So that becomes TOLIST method, TOLIST. Sweet. Now that was a good use of Google, everybody. And that's what you'll have to do when you're taking a test. So I now have a Weibull plotting position, generate quantiles, make a quantile plot, okay to copy from lab. So I need to make to plot. Okay, Weibull PP, and I want to use before list. And I don't actually have a density, so let's just repeat those. Okay, so I'm using my make to plot function that I've defined earlier. Make to plot expects information for two plots. So I'm just going to plot the same thing twice. So if there is a red and blue line, they should fall right on top of each other. And my title is empty. So there is our plotting position for the before. And what we really want to do is make a second Weibull plotting position for after, because we actually can be kind of sneaky. And this picture here is our empirical cumulative density function for evaporation before 1985. So at a value of 1, the probability of observing evaporation of 8.9 or smaller is almost assured. It's 1.0. The 50th percentile is a value of just under 4 or smaller. We have a 50% chance of observing that range of values. If we go to our lowest point, the chance of seeing 1.25 or smaller, very, very low probability. There's only one instance of that in the historical record. So that's our quantile plot. Our next thing that we would want to do is fit a normal distribution data model. So let's see how to do that. I think we have that done. We're going to need our normal distribution function. Let me see if I can find it. Normdist. Where is normdist? There he is. What normal density and normdist. So I'll need those from our lesson. There's our normal distribution function. And now we have to remember how to fit it, but we've already done that in lab. So we will get our fitting values. In this case, what we need is before list. List object has no attribute mean. Of course it doesn't. Oh, crap. Well, actually, we should be able to get that from our work up here. The before list, the mean value is 4.202. We'll just go ahead and hardwire that. I will leave it up to you to figure out how to do it because I'm running out of time. And our sample variance is just the square of the standard deviation, 1.77. Copy that, paste it here. So now we have the information we need to fit a model. And let me see where to get the model fit. I think that'll give me my model. And we're going to have to modify the x high at some point. Let's go ahead and see what happens. Mu is not defined. And you guys will have quite a bit more time to struggle with this than I do. Okay, so that's now fitted. And let's go ahead and try to plot these again. I'll take that same plot right there. And we will fit them. Okay, so now I want to plot X, Y, C, D, F. Okay, so my model needs some work. There's my data model in red. Oh, I've got the wrong Y, C, D, F versus X, just like the lab. And there's a model fit. And so we would repeat that for the log Pearson, the gamma model, fitted model, plot the things, choose the best model, capture the parameters, and estimate at quantile 0.99. Remember, we're doing that for before and after. So if we wanted the 99th quantile, we can use our norm dist function that we already have. And make sure I got it right. Yeah, norm dist is a distribution. So I'm gonna copy that. We'll go ahead and just do it for norm distribution, and you can read the lab and do it for whichever you prefer. So sample mean, sample variance, and we want to put it x of 9. We're trying to get y value to equal 0.99. So let's let it run once. So y value 0.93, that means x has to get bigger. So make x bigger, 0.96. I'll stop at 11.9. There we go. We're 99 0.27 percentile. And so what that is, our 99th percentile, or the probability of observing values of 11.9 or smaller, is 99.27%. That's taken from the red curve. Now this red curve is arguably not a great fit of our blue observations, but that's the idea behind this particular type of problem. So you're not going to have this exact problem, but you'll have something similar to it. And the steps will be laid out in the same fashion. You'll have data, you have to acquire the data, describe the data, break the data into two parts, plot the two parts, analyze one part, analyze the other part, and then make some conclusions based on your analysis. And that's pretty much what the kinds of problems you can expect on this exam are. So everybody went silent because I guess they're thinking about food. I'm about to shut this down. So are there any questions before I close it?
No, no questions.
Okay. Well,
That's all the exam.
that was a review. Pretty brutal. Looks like I recorded it, so I will post the recording, and then the worksheet I have here, I'll make a PDF image of that so you can go take a look at it and make sure there's no surprises left at the bottom. You might want to look at how to save Farang. I'm not going to tell you this. This is a personal favorite exercise. Just hopefully even if you're not a Star Trek fan, on some of these, the Kobayashi Maru approach is often the best approach. So take that to mind when you get to that. All right, well, that was supposed to be a two-way workshop. It looks like it was more one-way, but you'll have a video recording and you'll have an example of some worked problems that will be similar to what you'll encounter on your examination. Any other questions? Sorry for the interruption in the middle, but it was boss, so you kind of have to answer those. And Farang's grinning, he knows exactly what I mean. And the rest of you will as you move on in your careers. So we will see you on Tuesday. The plan for Tuesday is supposedly a review prior to the test. That'll be another question and answer session. So that'll be your last chance to kick the cat. That'll be me, the cat. And then we will have the in-class multiple choice, and then the take-home exam, which will be somewhat like what we just went through. All righty, well, everyone looks pretty weary, so good evening to you all. There's still a little bit of sunlight left, so you can go out and enjoy what turned out to be a pretty nice day, and then have dinner, watch some bad television. You got Star Trek Next Generation, Deep Space Nine at 9, 10, and 11 o'clock on H&I channel. I bet you in one of those 3 episodes, there will be some mention of Kobayashi Maroon. So, and I don't know what the episodes are tonight, but it's terrible that I found that TV channel because it pretty much ruins my Sunday nights. I actually have them during the week. Oh, Enterprise, which was in timeline actually preceded everything. That's actually my favorite of the 4, because there's original Star Trek, which I like. Voyager, which is good. Next Generation, which is good. Enterprise, which was great. And Deep Space Nine, which is good. So you can really ruin an evening. All righty. Well, good night, everybody.
Thank you. Good night.
Thanks.
Good night.
Have a good evening. Bye.
Bye-bye.